For centuries, we have operated under the assumption that the universe is built from tiny, solid spheres, solid bits of matter that serve as the foundation of everything we see. This classical model of physics relies on particles like electrons and quarks to act as the fundamental units of reality. In this view, if you break an atom down far enough, you eventually hit a single, indivisible point. String theory suggests that if you go deeper, the dot disappears. At the absolute bottom of reality, these particles are replaced by one-dimensional loops of vibrating energy. Every piece of the cosmos is woven from these identical threads, with the diversity of the universe emerging not from different materials, but from different rhythms. You can understand this through the mechanics of an acoustic guitar. A single string can produce a wide range of notes depending on the speed and frequency of its vibration. In quantum physics, a string vibrating at one frequency manifests as an electron. With more energy, it appears as a photon. This logic even accounts for the graviton. By vibrating in a heavy ripple, the string generates the gravitational force holding galaxies together. This unified cosmic symphony is mathematically elegant, but it comes with a physical requirement that challenges our most basic perceptions of the world. To make the mathematics of these vibrations work, we have to rethink the structure of physical space itself. In our three-dimensional world, strings can only move in a few directions. But to account for every known particle and force in the universe, the math shows that 3 dimensions do not provide enough room for the strings to vibrate. Standard string theory requires 10 dimensions to function. Its more comprehensive successor, M-theory, demands 11. M-theory is a hypothesized 11-dimensional model that aims to unify all 5 different versions of string theory. We only perceive 3 spatial dimensions: height, width, and depth. If 7 or 8 others exist, they are completely invisible to our senses and our tools. This is possible if those dimensions are curled up. Imagine folding a large sheet of paper repeatedly until it becomes a tiny, dense speck. The surface area is still there, but it is now too small to see. The three-dimensional universe we navigate functions as the outer skin of a much more complex, folded geometry. These hidden dimensions are shaped into highly specific structures called Calabi-Yau manifolds. A Calabi-Yau manifold is a complex geometric shape that allows the extra dimensions of string theory to be compacted into microscopic spaces. Much like the curves of a brass trumpet dictate the pitch of the note, the physical geometry of these manifolds restricts how a string is allowed to vibrate inside them. This means the shape of the hidden dimensions directly determines the constants of our universe, from the mass of an electron to the exact strength of gravity. However, the equations do not point to one single ideal shape. Instead, the math allows for a nearly infinite variety of dimensional configurations. Because the shape defines the physics, every possible configuration represents a universe with an entirely different set of natural laws. The scale of this variation is staggering. There are roughly 10 to the 500th power possible shapes for these extra dimensions, a number so large it dwarfs the total number of atoms in the observable universe. This is the multiverse problem. Because string theory predicts a massive landscape of potential universes, we currently have no way to calculate why our specific physics exist instead of trillions of other possibilities. To bridge this gap, the theory relies on supersymmetry. Supersymmetry is a proposed property of nature that suggests every known elementary particle has a heavier, as yet undiscovered partner particle. Detecting these partner particles would provide the first physical evidence that string theory aligns with our observable world. Yet, despite years of smashing particles together in these massive underground tunnels, researchers have never observed a single supersymmetric particle. String theory successfully resolves the mathematical conflict between the gravity of massive objects and the quantum behavior of atoms, yet it remains isolated from any experimental proof. We are currently at a scientific crossroads. String theory remains our most comprehensive attempt to unify all of physics, yet it exists in a realm beyond our current ability to measure. Without a way to test these predictions, the theory functions as a mathematical model of what the universe could be, rather than a proven description of what it is. This leaves us with a difficult question. Have we discovered the underlying code of reality, or just a sophisticated mathematical mirage? The music of the universe may be playing in these hidden vibrations, but for now, we are still building the tools required to listen.